what we're looking at here is the effects of both resistor variations and op-amp variations in our circuit. And if those two are in occurrence, what we're going to find out with, what we should find out is, what does the your common mode rejection ratio of the actual op-amp that you've got compare with the tolerance of the resistors that you're using in circuit to create like a system-wide common mode rejection ratio. So where we started from before, V plus is the positive input terminal, and that's been derived here as before, and V negative, the impedance at the inverting input, is this term here. Therefore it's quite trivial for us to write out V out in terms of AD, differential mode gain, and common mode gain for the two inputs, V plus and V minus, in our circuit, where we're looking at the differential gain and the common mode gain. So now what we need to do is we need to substitute all this together and see where we go. So here we start with V out. My output voltage is equal to AD differential mode gain, and I'll need my two input signals, V1 and V2. That is V1, R4 plus R3, minus V out, R1 over R1 plus R2, minus V2, and we've swapped over the resistor R2, R1, as we showed in that little trick the time before. So now I've got differential gain times input voltage 1 minus the output voltage minus the second voltage. Okay, we've got that there because we've got that feedback resistor, as we noted before with the way that R2 and R1 interact. Now we need our common mode gain, so we're now looking at ACM. What's my common mode? Well, I add my signals together, so I've got V1, R4 plus R3. That's my first term, and now I'm going to add into it my other term, which is now V out, R1 over R1 plus R2, and I'll add to it again as well, V2, R2 over R1 plus R2. Okay, so here I've got my first voltage, my second voltage, first voltage, second voltage, in terms of ACM and in terms of AD. Now if I want to rearrange to get this in the form of V out in term is equal to A V1 plus B V2, I can then put it into my common mode rejection ratio equation, if you remember. We will end up with V out 1 plus R1 over R1 plus R2 into AD minus ACM over 2 is equal to V1 AD plus ACM over 2 with a fraction R4 plus R3 plus V2 into, this time ACM, my common mode gain, over 2 minus AD, differential mode gain, and we have a fraction here, this is R2 over R1 plus R2. Okay, I suppose I should really have a bracket there, and there, second bracket there, and there. And as we remember before, common mode rejection ratio is equal to a half into A minus B over A plus B. So if you substitute now, this is A, and if you substitute this is effectively B into those terms, we'll get a new expression for common mode rejection ratio in this format. So here we are, common mode rejection ratio is a half. Now these expressions are going to get quite complex. we're taking this term here, ADACM over 2, R4 over R4 plus R3. So that's my A term. Let's write that down. There's the first part. Here's my fraction. That's A, and we want to subtract from A, B. And this term over here is B. So we have ACM over 2 minus AD, and we have a fraction on that, R2, R1 plus R2. Put second brackets around them just to make it clear. Okay, so we've got A minus B there. Now what we need to do is A plus B on the bottom. So we're going to copy those out, and the only sign that's going to change is this sign here, which is the minus from the A minus B will become A plus B. So the denominator, AD plus ACM over 2, with a fraction, R4 over R4 plus R3, plus this time, ACM over 2 minus AD, R2 over R1 plus R2. Okay, and we have our modulus right of that. So we've actually arrived now at an expression that's quite straightforward in terms of V1 and V2, in terms of common mode rejection ratio. Now we need to do a little bit of expanding to actually work out exactly what that's going to mean. So, common mode rejection ratio is a half into, we're taking the terms out, so we've got AD, R4 over R4 plus R3, plus R2 over R1 plus R2. There's our differential mode term, plus our common mode term, ACM over 2. And again in that terms we have R4 over R4 plus R3 minus R2 over R1 plus R2. Okay, and of course that's not finished, that's only the numerator, all divided by differential mode gain, R4 plus R3 minus R2 R1 plus R2 plus ACM over 2 into R4 plus R3, and again here the sign is now going to change. This is an R2 over R1 plus R2. Close brackets for that term. So now we've got quite a complex expression. What I'm going to do, I'm going to multiply inside this term by R4 over R3. So cross multiply. If I cross multiply this term in terms of R1 and R2, I'm going to end up with terms of R1, R4, R2, R4, R4, R2, R3, R2. Okay, and in this term I'll get R1, R4, R2, R4, R4, R2, R3, R2. Okay, so this is going to get quite complicated. Hopefully I'll get it right. Common mode rejection ratio is a half into differential mode gain, R1, R4 plus R2, R4 plus R2, R4 plus R2, R1, R3. Okay, plus ACM over 2, and the expansion inside this one's going to be R1, R4 plus R2, R4 this term minus R2 R4 minus R2 R3. That's the numerator expanded. Let's do the denominator. Okay. Expansion on the denominator, R1 R4 plus R2 R4 minus R2 R4 minus R2 R3 plus common mode term ACM. We have here R1 R4 plus R2 R4 plus R2, what's going on there, R2 R4 plus R2 R3. Now, as you can see in here, we're going to have things that are going to cancel. R2 and 4 will cancel. On the numerator here we've got R2 R4 twice, so that's going to double. We're going to get a 2 factor. And in 2 and 4 here those will cancel. So again, we're going to have cancellations and simplifications to do. So let's keep going with our common mode rejection ratio. Equal to AD. Our numerator contracts a little bit. R1 R4 plus 2 R2 R4 plus R2 R3. So we've collected this term here and this term here in the 2 terms, and ACM over 2. In this one, 2 terms actually effectively cancel. We lose the R2 R4 R2 R4 so we end up with R1 R4 minus R2 R3. That term's a little bit simpler. And we divide that by AD. In this AD here, because we've got the negative, we've got the cancelling here, so we've got R1 R4 minus R2 R3 plus ACM over 2, and in this case it's not going to cancel. If we look at the denominator here, R2 R4 are going to sum together, so it's like the numerator over here. We effectively have R1 R4 plus 2 R2 R4 plus R2 R3. So we've actually got a slightly simplified equation now. What we're going to need to do now is we need to actually make a little bit of a sort of a leap here in this term. Let me explain. If we divide in the numerator by R1 R4 minus R2 R3, this term here, it has that as the denominator, and this term is 1, ACM over 2. If we do the same thing in the denominator here, and we're looking at this ACM term, if we divide through by that term in both sides, the AD becomes 1 and ACM becomes this term over another value. Well, when we do that, we actually notice we get a simplification. So here's the simplification. Common mode rejection ratio is a half into AD differential R1 R4 plus 2 R2 R4 plus R2 R3. I'm going to put that in brackets. All divided by R1 R4 minus R2 R3. So I'm left with ACM over 2 there. Okay, that's just the numerator. Let's look at the denominator. the denominator becomes AD, differential mode gain, plus ACM over 2 into R1 R4 plus 2 R2 R4 plus R2 R3, all divided by R1 R4 minus R2 R3. What's happened here now, we need to have a look at this portion of the equation, this bracketed term, and see what does that actually remind me of. Well, if we remember before, from CMRR of resistors, we remember that a half into R1 R4 plus 2 R2 R4 plus R2 R3, all divided by R1 R4 minus R2 R3, is the common mode rejection ratio of resistors. We went a little bit further with that equation, but this is where it actually breaks out from. We went a little bit further and simplified and said that all the resistors are equal or in effect equal. But now, if we know that the common mode rejection ratio of resistors is this term, if we go back into this top expression, we've got AD multiplied by resistors plus ACM. We've got AD plus ACM multiplied by resistors. We've got products over sum. So the common mode rejection ratio is equal to a half into 2 AD, differential mode gain, times the common mode rejection ratio of resistors plus ACM over 2, all divided by AD, differential mode gain, plus ACM multiplied by common mode rejection ratio of resistors. Okay. Now, that is starting to look like product over sum. So it's almost equivalent to parallel resistors. Okay, so you can see where the simplification is going to come from in this design. We have common mode rejection ratio equal to a half into 2 AD upon 2 CMRR resistors plus a half. We've taken the sorry, that's the ADM over there, that's ACM over there. We've taken the ACM out, so we've got this half term here. If we divide that through, we divide by AD over ACM plus common mode rejection ratio of resistors. Now, common mode rejection ratio of the opamp is equal to AD over ACM. So this term here and this term here is effectively the common mode rejection ratio for the opamp. So we're now left with CMRR is equal to a half into 2 CMRR resistors times CMRR opamp plus the half, all divided by common mode rejection ratio of the opamp plus common mode rejection ratio of the resistors. We can now make a simple approximation. We can say that the half here is not significant. Why can we say that? Well, CMRR resistors and CMRR of the opamp is going to be significantly greater than the half. So we can throw the half away. If we do that, we now end up with the common mode rejection ratio for this system is going to be equal to as we've got a 2 on the top here, we can get rid of the half. It's going to be equal to common mode rejection ratio of the resistors times the common mode rejection ratio of the op-amp, all divided by common mode rejection ratio of the resistors plus the common mode rejection ratio of the op-amp, which is exactly the same as, or can be approximated to, CMRR resistors is in parallel with CMRR of the op-amp. And here we have arrived at quite a fundamental equation. This bit here is very important. It basically means that if your common mode rejection ratios are equal in resistors tolerances and your op-amp, you're going to get half of your common mode rejection ratio. If you want to maximize the resistor tolerances and get a very large value, you need to make sure that your resistor tolerances are as large as humanly possible and your op-amp is, say, an order of magnitude greater in raw terms, not dB terms, than your common mode rejection ratio of your resistors. In doing so, you can tend towards, and this is sort of like a guideline I would use, but when you use it I would always make sure you do this. I would say if CMRR op-amp is significantly greater than CMRR of resistors, then the CMRR of the system will be approximately the CMRR of the resistors alone. And again, that's an approximation that you can use, but you've got to know where it came from and you've got to know how to derive it. But you can only do that if the op-amp's common mode rejection ratio is significantly greater than that of the resistors. Well, that ends this particular screen cap looking at common mode rejection ratios.